Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be focusing in on how much valence electrons really like to be near the nucleus. And this is actually kind of a tricky idea because it's balanced of two major features. First of all electrons love nuclear charge. However, it turns out that electrons hate each other. And so when we're looking at valence electrons, we have this balancing act of they want to be near the nucleus, but they have to stay out of the way of all the other inner shell electrons. And we measure this using what's called the effective nuclear charge. So let's say I've got a nucleus like carbon, which has 6 protons. Well, if I've got an electron that's sitting out in the 2s or 2p orbitals, how much of that charge do I actually feel? And this is kind of a little bit difficult because what ends up happening is that my 2p electron is going to want to be near the nucleus, but it's going to be repulsed from my 1s orbitals, which are going to essentially counteract some of this attractive nature. And so we kind of change our language and think of this as an idea more of screening. So what ends up happening is that our inner core electrons more or less cancel out part of that charge. So what ends up happening is for each core electron I have, it cancels out somewhere between 0.8 and a full positive nuclear charge. However, my valence electrons will feel a little bit of that remainder. However, it also is worth noting that if I've got a 2p orbital, it's also going to be repulsed by my 2s orbitals. And so what ends up happening is valence electrons tend to screen out somewhere under about 0.3 or a third of a positive nuclear charge. Most of the time, a little bit less. So what ends up happening is that as I add more electrons into the system, I'm going to be screening out more and more charge. As I have more core electrons, I'm going to be screening out more and more of my overall charge, but there's also going to be more charge to be screened out. And this leads to some kind of fun effects. And generally what this means is as I move across the periodic table, I'm adding more nuclear charge than I'm screening out. And so my effective nuclear charge increases. And we see a very similar effect as I go down, as I will be adding more nuclear charge than I'll be screening out, because I screen out most of the nuclear charge, but not all of it. And then the final really tricky part is that it turns out not all valence electrons are screened equally. So let's go ahead and take a look at the 2s versus the 2p orbitals. Well, it turns out that my s orbitals kind of win on both ends because they're further out, which means they have less electron-electron repulsion like I have in my 2p orbitals, but also they have this little bit of density very near the nucleus that kind of tends to stay out of the way of both core electrons and my other valence electrons. So s orbitals are very good at penetrating through this screening effect. And p orbitals, not that great, but better than d. And this leads to some very cool effects. So if I have, say, hydrogen, I have literally no screening effect. If I go to helium, well, each of those electrons doesn't feel the full brunt of my 2 nuclei, but they feel most of it. Each one has about a third of the charge screened out because those 2 electrons get in each other's way a lot. However, when I go to lithium, well, now I've got 2 core electrons and 1 valence electron. So that 1 valence electron has most of that nuclear charge screened out. So those 2 core electrons screen out a full about 1.7 of my nuclear charge, leaving just a little bit left. However, when I go to beryllium, now I've got 2 valence electrons that feel about 2 charge. Ooh, that's barely better than helium. However, when I go to boron, now the numbers start getting a little bit better till we get to something like neon. It's got 6 valence electrons, all of which almost feel that full 6 nuclear charge. And then we go back to sodium and my effective nuclear charge drops again because I have a whole new set of core electrons all screening out my one lonely electron. Also, if we take a look at, say, our core elements like oxygen, what we find is that the s orbitals have a slightly higher effective nuclear charge than the p orbitals. And this is due to that penetration, which means that those s electrons are going to be slightly lower in energy than my p electrons, which is, again, what we see with our filling diagrams. So this really does help explain our filling diagrams, as well as how much each of the electrons wants to be in each of these atoms, which is going to dictate a lot of reactivity. So this is one of the reasons why everybody kind of likes to be a Nobel gas, because they have less of that effective screening than an electron almost anywhere else does. So for example, look at fluorine's very high effective nuclear charge, much better than oxygen. So it's got more nuclear charge to bring in an extra electron. Whereas lithium barely has enough nuclear charge to hold on to the one it has. And so these trends in effective nuclear charge tend to dominate a lot of trends in reactivity. Again, noting that as we go across, effective nuclear charge increases because I'm not perfectly screening because all my valence electrons don't perfectly screen each other. And as I go down the periodic table, my effective nuclear charge increases because the core electrons also aren't perfect at screening. And while I am adding more electrons, I'm adding more nuclei faster. And again, we see very similar trends with, it is worth noting that as we go to d orbitals, those d orbitals are very close to the nuclei, much closer than the s orbitals, so they have a much greater effective nuclear charge. However, this can be a little bit misleading when you're looking at the stability of those d orbitals versus the s orbitals, because they are so tightly packed in close to the nuclei that they have to deal with all of the other features of there's other electrons sitting there in the way. So in general, d orbitals are, we tend to fill the s shell before the d. All right, so one of the other features we have to worry about is while the effective nuclear charge gets increases as we go right and down in the periodic table, this doesn't mean that my electrons are still going to be the same distance from the nuclei. So next time we're going to be looking a little bit more at electronic and atomic radii. Until then, take care.